Okay, hi AP class. This is your lecture for September the 30th, Monday, and this is the video. What I'm asking you to do for homework is just watch this video, take notes on the examples, and that's it. If you want to push ahead with the assignment sheet I gave you, you can. But we'll work on that in class tomorrow as groups, and I told you you'd be doing group work tomorrow on that. So what is the purpose of an empirical formula? Okay, so empirical formulas are an intermediate step to finding the actual molecular formula. That's the formula that we would normally use in a chemical equation. It's how many atoms of each of the elements goes into a particular compound. A molecular formula is the actual formula of the chemical compound. So we often will use laboratory data to figure out an empirical formula and then use the empirical formula to figure out the molecular formula. So let's go on to understanding what an empirical formula is. An empirical formula is the smallest whole number ratio of atoms of each element in the molecular formula. So empirical formula is the formula a chemical compound that shows the smallest ratio of its elements. So example, what is the empirical formula for butane, C4H10? So that is an actual molecule, hydrocarbon molecule, has 4 carbons and 10 hydrogens. But the way you get the empirical formula is by reducing it like a fraction. So divide through by 2, and what you get is C2H5. That's the empirical formula for butane. So there's no actual molecule with the formula C2H5, but this shows the simplest relationship between the number of carbon atoms and hydrogen atoms. Okay, so what are the empirical formulas for the following compounds? So for H2O, well, for H2O, it's already reduced as far as you can reduce it. It's 2 hydrogens to 1 oxygen, so that's H2O. For NSE4, you can reduce that down to, you divide through by 4 and you get NSE. In other words, there's 1 nitrogen for every selenium atom. And C2H6, the empirical formula is CH3. So there's 1 carbon for every 3 hydrogens. Again, there's no CH3 molecule, there's no NSE molecule, but that's just showing the ratio, the smallest whole number ratio of the elements in that particular molecule. So using laboratory techniques that you will learn, you can determine the number of grams of a product in a chemical reaction. So using the grams of products, you can compute moles and then the empirical formula. So this is an example of one of the 5 reactions we're going to study this week. A decomposition reaction is one in which a compound is broken into its elements. An example is nitrous oxide is NO. You can break that into nitrogen and oxygen. By measuring the mass in grams of the nitrogen and oxygen that you get from this reaction, you can determine the empirical formula of NO. In other words, what the subscripts of N would be and what the subscript of O would be. Okay, so let's take an example, and this is the best way to learn how this works. So we're going to do a decomposition reaction, or we did do a decomposition reaction that produces 1.443 grams of selenium and 5.841 grams of bromine. What is the empirical formula of SEBR, this SEBR compound that was decomposed? So the first step is you compute the moles of Se and Br using the molar masses. Okay, so you have 1.443 grams of Se, and you take the molar mass of that to figure out the moles of Se. And you end up with 0.018 moles of selenium. You do the same thing for bromine. Take the grams that you were given, use the molar mass conversion, and you come up with 0.073 moles of bromine. All right, so the next step is you create a ratio of the number of moles for each element you obtained and place the smallest number of moles you computed on the bottom of the ratio. There's actually just 2 in this particular problem. There's 3 in a later problem. So selenium, that was the smallest number of moles of those two compounds. So you just create a ratio of 0.018 over 0.018. The smallest one is always going to be its number of moles over its own number of moles. It's always going to be 1 to 1. And then bromine, I put that up there for the class so you can see it in class, is 0.073 over the number of moles of selenium, 0.018. So next you divide the top number by the bottom number and place a 1 underneath the quotient. So we have 0.018, 0.018 is 1 to 1. And 0.073, 0.018 is 4.05 to 1. And what you're looking for is a whole number, not a decimal number. But this decimal number is very close to a whole number of 4. So we're going to accept that as being close. The reason you might have some error is there's always error in laboratory measurement, and you probably didn't get exactly the right mass in grams of bromine, so it might be a little bit off. If it's more than about 0.1 in either direction, then it's probably too much, and you don't want to accept that as being a whole number. So the next thing you do is you multiply the top and bottom of the fraction by whole numbers until you have a whole number on the top and the bottom. And note that the number on the top might be very close to a whole number, but not exactly a whole number. That's what we just saw in this example. So we're going to say that 4.05 is approximately 4, and those are whole numbers. So that you do that when you just multiplied them by 1. So you didn't need to do that in this exercise. So you'll see an example of that multiplication that we're talking about here in a later example. So you have a 4 to 1 ratio. So then you place these numbers as subscripts of the elements, and this is the empirical formula. So SeBr4, you had 4 bromines and 1 selenium, so that's the empirical formula for SeBr4. That is the empirical formula. Keep in mind, this is not the molecular formula, not the actual formula of the compound necessarily. It might be, but it could also be any multiple of this. It could be Se2Br8, it could be Se3Br12, but the empirical formula is SeBr4. That's the smallest ratio of the atoms to each other. Is a 1 to 4 relationship. Okay, let's do another one of these. So a decomposition reaction produces 1.651 grams of silver and 0.122 grams of oxygen. What is the empirical formula of the silver oxygen compound that was decomposed? So see how many of these steps you can do on your own. What's the first thing we do with the grams? Okay, we can never work with grams in chemistry in a chemical equation or a chemical formula. So what do we have to do? We have to convert to moles. So we're going to do that. And we have the molar mass conversion that you can see right there for silver, using the molar mass that you get off your periodic table for silver. And then for oxygen, we're only using a single oxygen atom here, not the O2 oxygen molecule. So the number is 16 grams for oxygen. Do that molar mass conversion, you get 0.0077. So now identify which of those two numbers of moles is the smallest. And the smallest would be 0.0077 moles of oxygen. So what's the next step? See if you can do that on your own. And let's proceed. And so you create a ratio of the numbers of moles for each element you obtain. Place the smallest number of moles you computed on the bottom. Again, it's not 3 ratios here, it's just 2. And so what you have is that for silver, and you have that for oxygen. Remember, the smallest number of moles is always going to be that number over itself. So we divide top and bottom, we put a 1 underneath, and when you divide 0.0153 by 0.0077, you end up with 1.98 to 1. And we're going to say that that's close enough to 2 that we're going to count that as being 2. For oxygen, it's just 1 to 1. So now you multiply top and bottom of the fraction by whole numbers until you have a whole number on the top and the bottom. Well, again, in this case, if we're going to round 1.98 up to 2, we really don't need to do that. We end up with a 2-to-1 ratio. Those are both whole numbers. So you place these numbers as the subscripts of the elements. This is the empirical formula, and that would be Ag2O. Okay, so that's just another simple example. Let's do another. And please put all of these examples into your spiral notebook. Okay, so combustion of an unknown hydrocarbon produces 33.01 grams of CO2 and 13.51 grams of H2O. Determine the empirical formula of the compound. So a hydrocarbon is a compound made up of carbon and hydrogen, and a combustion reaction burns a hydrocarbon and has the general formula: some hydrocarbon, the subscripts can change, there's quite a few different types, plus oxygen. So you light a match to that. And then what that produces as products is carbon dioxide and water. So you're going to see this type of reaction quite a bit in this class. Okay, so there's the reaction. So we're going to let's start off with carbon dioxide. So what we're trying to find out is how much carbon and how much hydrogen are in that hydrocarbon. So what we can see from this chemical reaction is that all of the carbon in the hydrocarbon, the CH compound, went into the carbon dioxide. That's the only place you see a C over on the right-hand side. So whatever number of grams, whatever number of moles is on the left for carbon, has got to be the same number of grams or the same number of moles on the right for carbon. So what we're going to do then is the first thing we always have to do is convert grams to moles. So we start off, there's our grams of carbon dioxide. We use our molar mass conversion, which for carbon dioxide is 1 mole of CO2 for every 44.01 grams of CO2. And we can show that on our diagram from here. And what that gives us is 0.75 moles of CO2. Now what you have to do is figure out how many moles of carbon. We're not interested in CO2, we're interested in just the carbon that's there. And this is something we haven't done in our previous problem sets. So what you can see is that there's 1 carbon atom for every carbon dioxide molecule, or there's 1 mole of carbon for every mole of carbon dioxide. It takes 1 mole of carbon atoms to make 1 mole of carbon dioxide. So it's a 1-to-1 relationship. So that forms our second conversion. So this is something you haven't seen before. 1 mole of carbon over 1 mole of CO2. In other words, you're figuring out the moles of a specific element in that compound for every mole of the compound. And if you do the math, everything there cancels out, and you end up with moles of carbon. And that ends up to be 0.75 moles of carbon. It's a 1-to-1 relationship. What that means is over on the left-hand side, in the hydrocarbon compound, we have 0.75 moles of carbon to start with. Now we do the same thing for hydrogen. Okay, so you look at the hydrocarbon compound, it has a hydrogen, and the only place hydrogen appears on the right-hand side is in the water, H2O. So we do the same type of calculation. Stop the video and see if you can do this calculation by yourself. One thing you want to note is that there's an H2. It's not like C where there was only 1. There's 2 hydrogen atoms for each water molecule. So see if you can write out this equation, dimensional analysis equation. Okay, so we start off with the number of grams that we were given, 13.51 grams of water. We do our molar mass conversion, and that's 1 mole for every 18.02 grams. So now we know that we have 0.75 moles of H2O, same as we had for carbon. It doesn't always have to be the same, it just happened to be in this problem. Now what we got to do is figure out how many moles of hydrogen atoms we have for every mole of water. And you can see that you need 2 hydrogen atoms for every molecule of water, or you need 2 moles of hydrogen atoms for every mole of water. So we're going to do that conversion. So it's 2 moles of hydrogen over 1 mole of H2O. And if you do the math, you end up with moles of H, and that's 1.5 moles of hydrogen. So now we see we had 0.75 moles of carbon and 1.5 moles of hydrogen. So you can see that's the ratio of hydrogen to carbon. And just by inspection, just by looking at it, you can see it's a 2-to-1 ratio, 1.5 to 0.75. If not, you would have had to do the procedure where you multiplied 1.5 by 2, 0.75 by 2. That would have given you 3 on the top and 1.5 on the bottom. That's not whole numbers. So then you multiply by 3, you'd end up with 4.5 on the top, and you'd end up with 2.25 on the bottom, still not whole numbers. So now you go up to 4. 4 times 1.5 is 6 exactly, and 4 times 0.75 is 3 exactly. Those are whole numbers. So that's a 6-to-3 relationship, or just like reducing a fraction, you reduce it down to 2-to-1. But I think this one was simple enough that we didn't have to do that process. So it was 1.5 over 0.75 is a 2-to-1 relationship. So you have twice as many moles of hydrogen as carbon. So the empirical formula is CH2. Okay, and that takes care of this lesson. This is all you're really asked to do tonight. If you wish to proceed, I want you to have the assignment if you want to do it. I wanted to give you some time in class. There just wasn't time, so I wanted to walk you through this lecture. But in about 17 minutes, we were able to get through this. And what you should come in class tomorrow is having seen this, having taken notes in your spiral notebook, and then we'll work on that assignment. If you do decide to do this assignment at home tonight, I can give you kind of an extra assignment to do, and you can do that instead. We'll also have a small project in class tomorrow, and maybe a couple other things. All right, so you have a good evening, and we'll see you tomorrow.